So this unusual light pattern meant that there was something wrong with physics. The physics at the time, it was called classical physics or Newtonian physics. And classical Newtonian physics predicted that the hydrogen lamp should emit white light. There should be nothing about the electron preventing it from absorbing any energy it wants to. The hydrogen just consists of proton and electron. And so what about the structure of the hydrogen atom is causing it to only allow the electron to move at certain speeds or to oscillate at certain frequencies, etc. And so, in other words, something had to, had to be done to fix this problem. All right, so people started working on it. One of the people who started working on it was Max Planck. The Planck's constant, that H is named after the Nobel Prize. Well, what he said is that energy is quantized. What quantized means is that energy is not continuous. But it's kind of tricky, you know. And so I don't want to get into the details now. But what I want to say is this. With Planck, what we get is this, that, in other words, actually let's not talk about Planck just yet. We'll talk about this here. With this, you know, we have a pattern here. And so what does the scientific method tell us to do if we have a pattern? We have a pattern, we try to figure out a mathematical formula or mathematical relationship that defines the pattern. And the mathematical relationship is often termed an empirical relationship or an empirical law. And so the mathematical relationship that defines the pattern that's seen for the hydrogen atom is called the Rydberg equation, the Rydberg law. But having a mathematical equation, does it tell us anything? No, we just have a mathematical equation that fits those lines. And so where does that, you know, where did that originate from? You know, and so the first person to come up with a hypothesis regarding, well, actually, probably not the first. The first person to come up with a hypothesis, I don't know, but the first person to come up with a theory was Bohr. Here. And so Bohr, that's Niels Bohr there, he came up with a theory. And this is his theory here. His theory was that the energy of that electron is not continuous. This is gravitational potential energy. And so for Bohr, the energy of the electron in the hydrogen atom wasn't like this. You can't have any energy. So this person can have any gravitational potential energy. They can stop anywhere between here and here. So they can have any potential energy here. What Bohr and Planck proposed is that they're forbidden energies. So for example, this person can have n equals 1, ground floor. Then they can have n equals 2. But can they have n equals 0.5? Can they go halfway up the step? No. Nor can they go 2.1, 2.2. In other words, the energy, the gravitational potential energy here is quantized, so they can be 1, 2, 3, 4, 5. 5 steps. Well, that's what Planck proposed. Planck actually won the Nobel Prize for something called black body radiation, which isn't discussed in the book. And this is where this equation comes in. You know, the equation, even continuous spectrum like the sun, whatever else, there's some unusual features of that were not predicted by classical physics. But Planck fixed those by assuming that energy came in these kind of packets. So the energy is proportional to n times the frequency, where n is 1, 2, 3. But you can't have 1.5, you can't have 0.5, you can't have 2.1. It's got to be 1, 2, 3, so it's going to come in these steps. And if you made energy come in steps like this, then you could explain some stuff that they don't even mention in this book. But, for which he won the Nobel Prize for. But we're going to skip that. We're going to go down here, talk about Bohr. So, okay, now how do you visualize this? Well, a theory should give you a fundamental description of what's happening. So this is Bohr's fundamental description of what's happening. You have the nucleus here in the center. And so the first step corresponds to what we call the first Bohr orbit. It's here, the n equals 1 orbit. And so this is the lowest energy state for the electron. If you want to make this electron go faster, this would be like a satellite orbiting the Earth. You know, if you have a satellite orbiting the Earth, you can make the orbit a little bit wider here by making the satellite a little bit faster. But it turns out you can't make it a little bit wider. You have to jump up to the next allowed orbit. And so any orbit between here and here is forbidden. And so it cannot, the satellite cannot go any speed between here and here. It has to jump up to this one. This would be called the n equals 2 orbit. And then it go to jump up to the next one, the n equals 3 orbit, and the n equals 4 orbit. This seems weird, but you know how many orbits there are possible? An infinite number of orbits, because we go from n equals 1 to n equals infinity. But if there's an infinite number of orbits possible, then does that mean there can't be forbidden orbits, can there? Because if there are an infinite number of allowed orbits, doesn't that take care of all the orbits? No. Oddly enough, there are an infinite number of allowed orbits, and there are an infinite number of forbidden orbits. And so we got a lot of orbits. And so anyway, so it behaves like this. Now, these are postulates. You know what postulates are? Postulates are taken without proof. And so, well, Bohr came up with the reason. So somebody might ask, why? Why can't I have an orbit, half the distance between these two? You know what Bohr said? Because you can't. It's a postulate. That's it. You take it or leave it, basically. And you take it because, what other explanation is there? Is that a great No, not really. Okay, that's in terms of orbits. Now let's look at that in terms of energy. And in terms of energy, these are like our steps here. But you can take a look at the steps here. These steps are even. These steps aren't even. So the first step is a big one. As we go from n equals 1 to n equals 2, it's a big step up. And then n equals 2 to n equals 3 gets smaller. 3 to 4 is smaller. 4 to 5 is smaller. 5 to 6 is smaller. So what happens is these don't diverge. N equals infinity is just right here. And so between here and here, there's an infinite number of lines. So you got to start drawing them very tightly spaced. But the biggest jumps are right at the beginning here, and that's where we really notice, because if this, what this means is that you need enough energy to kick it all the way up here. So if you try to kick it halfway here, it's not going to work. It's not enough to reach that next step. And so all these energies from here to here are forbidden. So the next allowed energy would be here. And so you need that. This would be the allowed energy that's enough to kick it from here to here. If you kick it too high, it's forbidden. There's just nothing there. And so that's what it means. You have to have forbidden and allowed. And this is what they mean by quantized energy. Quantized, it comes in these steps rather than continuous. And continuous would have, infinite number of steps here, all right next to each other, so it can jump as high as it wants or as low as it wants. It can go anywhere it wants. But here, it's not enough to. So that's the Bohr theory. Bohr was wrong. And so the Bohr theory was abandoned eventually. And the Bohr theory was replaced with quantum mechanics. And so the problem is we shouldn't even talk about the Bohr theory, really. Since the Bohr theory is wrong, a lot of people don't realize it's wrong, and they still talk in terms of Bohr orbits. It's totally wrong. Nobody talks in terms of Bohr orbits. Bohr orbits are long gone. The unfortunate thing is people don't really understand the quantum. And so when they visualize the atom, they visualize this. What they showed there are all the orbits flattened into a plane. The orbits don't have to be flattened into a plane. These are called spherical orbits. They can be in any plane. And so here would be the n equals 1 correct. This picture is much more correct over here. And so what this is this. It turns out that the Bohr theory couldn't make any predictions. So for example, if Bohr tried to predict the spectrum of the helium atom, helium has 2 electrons, it failed. In fact, Bohr theory failed for anything with more than 1 electron. It worked with anything that contained only 1 electron. Well, how many only 1 electron species are there? Hydrogen. That's about it, and some ions. Other than that, and so something had to be done because Bohr's theory wasn't working. Well, what had to be done was there are some developments that happened after Bohr. One of the developments that happened is this person, Broglie. Broglie talked about the wave characteristics of electrons. So de Broglie, what he's famous for is something called wave-particle duality. When you think about light, coming from the light bulb or from the sun, you think about waves. Well, I think about waves. But I don't think about particles of light, particles of light. Do you think about a whole bunch of little particles of light hitting you, necessarily? Well, maybe you do, maybe you don't, but maybe you should because of wave-particle duality. Sunlight comes in little particles, but these particles aren't like particles you normally think of. Particles you normally think of would have mass, and they're a physical entity. These particles are called photons, and these photons really don't count it. And so I gave you the equation for the energy for a particle of light, and that's equal to h nu. And so gamma rays have high frequency, and so the particles of gamma rays pack a lot of punch. They have a lot of energy. Radio waves have low frequency, so they don't pack as much punch. So this is another way of visualizing light. Well, it turns out that electrons, when you think about electrons, do you think about waves like light? No, you don't. You think about particles. When I think about electron, I think about a little tiny particle. I don't think about waves like light. But it turns out that electrons are very, very weird entities. In fact, electrons are nothing. You can't compare electrons to anything in this world because electrons are both particle and waves. Sometimes they behave like waves, like light. Other times they behave like particles, like atoms. And so they're very, very difficult to describe because physically they're nothing like anything that we understand in our physical universe. So if we think about electrons having wave properties just like light, then that's a significant development in quantum mechanics because what this does is it makes this whole idea of quantized, that is allowed and forbidden energy, much easier to understand. And one of the ways we try to understand it is by quantized standing waves. We see standing waves, in musical instruments like this. Let's say you have one string guitars like that. If you had a one-string guitar, can you play all note? Can you play high and low tones, or what they call it? If you had a one-string guitar, would that? And let's say there's no frets on it, so you can't change the length of the string. It's just one string attached here and here. You know what? How many different sounds can you get from that? Well, pretty much, guitars are kind of nice because you could shorten the string or lengthen the string using your fingers, right? But let's say you couldn't, and the string was attached here and it's attached here, and you couldn't shorten or lengthen it. It's just got one length. And then you pluck that string, there's only going to be one sound coming from that. right? And that's it. It'd be pretty boring. But that would be it. But it's not just one sound. There's another sound you can get from it if you pluck it a lot harder. If you pluck that string a lot harder, then there's the next allowed energy for that string. And so what that looks like is this. If we pluck it here, we get this sound. It's low frequency. If we plug it here, this is a little higher frequency. This would be its first overtone here. And if we pluck it even harder, this would be the next allowed. And so when we look at these and we look at the allowed energies, when we look at the allowed energies, lambda over 2, we can fit 1/2 wavelength in here. Half wavelength. Over here. Here we can fit 1 full wavelength or 2 half wavelengths. Here. The next allowed energy is we could fit 3 half wavelengths or 1.5 wavelengths here. But if we tried to fit 1/4 of a wavelength, it wouldn't work because 1/4 of a wavelength would start here and end here. It can't work in this. It's forbidden. And so anything, like if I tried to do 1.1 half wavelengths in here, it's forbidden. All those sounds are forbidden. And so if we visualize an electron as having wave properties, and then quantization comes naturally because here the electron is like confined in a box like this. We call this an electron in a box. Then there are going to be certain frequencies allowed and certain frequencies forbidden. Certain energies allowed, certain energies forbidden. And so here we see quantized energies of a guitar string or a musical instrument string or a standing wave. Now in terms of electrons, the same exact thing happens in terms of electrons with the world rate. We just never noticed it before. Classical physicists didn't notice this because the box is so huge. If you look at an electron, you know, the temperatures on the sun are so high that the electrons actually get ionized off the atom. If electrons get ionized off the atom, then they're free. And if the electrons are free, they're in a gigantic box, the sun. Right? And so if you're in a gigantic box, then it's going to look continuous. Because let's take this string, you know. This string, let's get in 1 billion half wavelengths in here. And so we're at n equals 1 billion. If we're at n equals 1 billion, 10 to the 9th, what's the next allowed energy? Well, the next allowed one is 1 billion and 1 half wavelengths. So the next allowed one is going to have 1 more half wavelength in here. So rather than having 1 billion, we have 1 billion and 1. What do you think? Is there a big sound difference between having 1 billion and 1 billion and 1 half wavelengths on that? No, this thing's so high frequency you can't even tell the difference, right? And the energy gap between fitting 1 extra half wavelength in there is so tiny, it appears to be continuous, right? Versus going from 1 to 2, there's a big jump here in energy. But in going from 1 billion to 1 billion and 1, there's a very tiny jump. And so even though the electron energy is quantized, you don't notice it because the box is so big. You only notice it when the box shrinks smaller and smaller. As the box shrinks smaller and smaller, let's go to a piece of metal. If we're at a piece of metal, a metal like tungsten behaves okay because the electrons in metals are loosely held. Let's do this. And the electrons in metals are in a big box. The electrons are tiny. This piece of metal is pretty big. And so this would be an electron in a big box, the metal. Electron in a big box is, okay, I don't know how many half wavelengths, but there's got to be a lot of half wavelengths here, right, for that electron. And so what I do is I can just warm it up a little bit. If I warm it up a little bit and I feel this, you know, even though I don't see much light, I can feel it. Do you feel? I feel the heat coming off this. I don't want to touch it because it's hot. You know what kind of heat? I can't see that heat, but I feel it. You know what heat that is? Infrared. And so what I've done is I excited the electrons to infrared,
and they don't stay excited forever, they're going to emit that infrared energy. If I heat this hotter, it'll start to glow. It'll start to glow because electrons are getting hotter and hotter. And do you see that? It's going red hot. Red hot. Eventually, if it gets hotter and hotter, it'll start to glow orange, and then yellow, and then white hot. It'll start to glow white hot. When it's going white hot, then it's emitting all the colors of the rainbow. And so here, this is what we call continuous, because all the colors of the rainbow are being emitted. Why? Well, you know, it's continuous because we don't have big gaps. These electrons are in a pretty big box, this piece of metal. In a hydrogen atom, in that hydrogen lamp that we were trying to build, the electron gets cut into a small box like this. And so here, this is allowed energy for the electron. The next allowed energy for the electron is this. The next allowed energy for the electron is this. And so what we see is there's going to be a pretty big jump in going from here to here. You know, it's like you have to pluck the string quite hard on the instrument to get to the first one here. Versus once you're up very high, then you have this. And so quantum physics was missed because most physicists worked on big objects. If you work on a big object, you're dealing with a big box, not single atoms. When you start shrinking down to single atoms, like in a hydrogen lamp, then we're working in very small boxes, so very small things, the wavelength becomes quite important. Whereas very large things, the wavelength is barely noticeable. Barely notice it. And so de Broglie, he won the Nobel Prize for this. All matter has wave-like properties. All matter has wave-like properties. And then there's another person, Heisenberg. Have you heard of Heisenberg? Heisenberg is very famous for what? Heisenberg is very famous for the uncertainty principle. You ever heard of that? The Heisenberg uncertainty principle. And so this is what it looks like to us. This is the Heisenberg uncertainty principle in action. If we just take the first orbit here, this is deceptive. If we take the first orbit here and move it over here, this is kind of what it looks like. This is the first allowed energy. And what this diagram means is this. I'm going to use the bird nest analogy. The bird nest analogy is we'll put a bird nest here, and we'll pinpoint the bird like every 5 minutes or something like that, days. And so, can you, if we put a bird nest there, can you tell me exactly where that bird is going to be 5 minutes from now? No, impossible. The bird can be anywhere. Well, not anywhere because it can't get too far from the nest, right? It doesn't have that much energy. And so this is the Heisenberg uncertainty principle. This is very different. If the electron were orbiting the nucleus like this, like a satellite, then 5 minutes from now we could predict where it's going to be because it's just orbiting over and over again. And so we can predict it. It's going to be up this path. But over here, it's not. And so if we don't have orbits, what we call this is an orbital. And the orbital is like this. 5 minutes it's here, put a dot. Next 5 minutes here. And so after a long period of time, we see the dot. And so the bird doesn't diverge or just go too far away from the nest. It stays pretty close to the nest. Sometimes it's out here, but not as common. So what this is called a probability distribution. It's the probability of finding electrons. Electrons like a bird in the nest. So it's got this energy. Now the next allowed energy is higher. And so the next allowed energy is just like the next allowed orbit. The next allowed orbit's higher in energy, so it's going to be farther out. Well, if the bird has more energy, then there's going to be a higher probability it's farther from the nest. And so the next allowed energy is going to look something like this, except it's going to be a lot bigger. The bird will be farther. And so when we're thinking about electrons in atoms, this is how we're going to start visualizing it. We're going to start visualizing it in terms of orbitals like this. And so with the Heisenberg uncertainty and de Broglie's wave properties matter, and Planck's quantization of energy, this guy came up with the mathematics or the equation of quantum mechanics. Schrodinger. And so this very famous Schrodinger equation. Schrodinger equation is the equation that defines quantum mechanics. That's what we have, the Schrodinger equation. So let me show you one thing. What we have is we have three-dimensional waves. This is a one-dimensional wave along the x. And then we have two-dimensional waves along the x and the y. And then we have three-dimensional waves, which are these orbitals. And so what do these things look like? This is what it looks like here. I think we're out of time, so I'll show this again. Just show you what it looks like. So just like a guitar string, right? This is like a drum surface. Forbidden, allowed. Forbidden, 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 allowed. Energy. Okay, then it goes forbidden, 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 and what's the next energy that's allowed? There, next energy that's allowed. And then forbidden, allowed. Forbidden, allowed. The salt on a plate vibrating at different frequencies. And so that plate also has forbidden energies and allowed energies, and this is what they look like, you know, with the salt shaker on there. Allowed. That's in 2 dimensions. Yeah, it is. In 1 dimension, it's not. It's just regular waves. In 2D, it looks like that. In 3D, it's like this, but with shapes. And so you can go through a whole bunch of forbidden and then allowed. You see? And so you can see the forbidden and allowed energies come right off due to the wave properties of matter. And this all deals with wave properties here. This is getting too hard to listen to. All right, that's it for today.
Oh, that's like 600. That is